In this video, we're going to talk about unit step function. This is another function we use in signals and system quite often to describe, mostly describe functions that change from time to time. They're quite useful. So let's go ahead and start first by the definition and some examples. So unit step function is always represented using u. So it's usually u of, in this case, if we go, let's start with the discrete time case. So it will be u of n minus n0. N0 could be any number from minus infinity to infinity, including 0. So n minus n0 is said to be equal to 1 as a definition of unit step function when what is inside the square bracket is larger than 0. So n minus n0 is larger or equal to 0, which basically tells us this is equal to 1 when n is larger or equal to n0. Okay, good. Now, all other time, the value of this is 0. Okay, we had talked about impulse function just a little while ago. This is basically a way of representing a whole series of impulse functions. But let's take an example of this. Let's do an example and see if we can draw and using the definition. So let's say someone gives us a step function that is n minus 3. And they ask us to show it. We know based on the definition that this is equal to 1 when what's inside is larger than 0, which means n is going to end up becoming larger or equal to 3. Which when we plot it, it says basically it's 0 all the way to when you get to 3. At 3, it goes up 1, and then it's 1 from then on all the way to infinity. Okay, so that's great. Now let's see if we can apply the definition in a very general form. Let's do just a quick another example, and this time let's go ahead and say our example is a little bit different. Is u of 3 minus n. So take a minute and see if you can come up with the definition of what that means if you have a function that looks like that. What is it saying to us? It's basically saying this is equal to 1 when, right, based on the definition, when what's inside the square bracket is larger than 0. So if you do that, now we see that n has to be less than or equal to 3 in order to be 1. Of course, I didn't write it for the previous one or here, but basically the other part is that otherwise, if this condition of n being less than or equal to 3 is not correct, it's 0. But notice what happened now. Now if this is n, this thing actually starts at 3 and it's 0 above 3, and then it's 1 all the way to minus infinity. Okay, so always remember the definition. The fundamental definition is that what's inside this has to be larger or equal to 0, and let that lead you to what the conclusion should be. Okay, one last thing before we go away. So now we know if someone gives us a general function, a step function of n minus n0, oops, and these have to be square brackets. So if you have a function like this, we can indeed write this in terms of delta, okay, of delta n minus k if we wanted to. And so the way we write this, for example, for this one is going to be a summation of n equal k equal n0 to to infinite. Those two are the same thing, so we can write them back and forth if you wanted to. On the other hand, if you wanted to, for example, someone wants us to represent delta n minus k as a function of unit step functions, we can do that as well. So what we could do is say this is equal to unit step function of n minus k minus u n minus k minus 1. Okay, so actually I got that backwards. Should be minus 1 in here, and this one doesn't have it. Okay. Because let's kind of find out what we got here. So in here we've got this thing. It says n larger than k plus 1, larger or equal to k plus 1 is 1. This one, n larger than or equal to k is 1. So actually what I'm representing here is actually n minus k minus 1. If you wanted to represent delta n minus k, probably better off doing step function of n minus k than subtracting step function of n minus k plus 1. In this case, this is going to become 1 when n is larger or equal to k. This is going to be 1 when n is larger or equal to k minus 1. So that was what I was going for, but along the way we learned about this one too. Okay, so now let's go ahead and take a look at a continuous time. The process of the continuous time is going to be very similar, but where we have summation, in the other case we're going to have integrals, and when we have subtraction, we're going to have derivatives. But let's start with the definition of a step function. And a step function basically can be written as t minus t0, where t0 is any real number from minus infinity to infinity. And once again, this is equal to when what's inside this bracket is larger than 0, which means t must be larger or equal to t0 for this to be 1, and 0 otherwise. Okay, so that's basically a representation of a continuous unit step function, and the mathematicians had to do a little bit of a work here because there is a discontinuity at t0. So this function, for example, when we have a function u of t minus 2, let's say, oops, you have that function as an example, and you're asked to draw that function. You'll say, okay, I know this function is equal to 1 when what's inside this parenthesis has to be larger than 0, which means t has to be larger or equal to 2, and it's 0 otherwise. So now what I can do is I can plot this. If this is t, we can plot this as being 0 all the way to 2, popping up, there's discontinuity, and then coming up to 1 and moving forward. Again, these are all called unit step function. Great. So the next thing would be, can we relate a unit step function in continuous time to an impulse response? Yes, we could do that. For example, if we were to integrate a function for, let's say you want to represent step function t minus 5, you want to represent that in terms of impulse. That simply is the integral of from 5 to infinity of impulse, because impulse was on one point in time and now you're just moving it, so it's going to be impulse of, again, remember we do taus here, so it would be t minus tau d tau. So as tau moves, the impulses moves with that, so you're going to get a continuous. So you basically are saying you're summing everything from 5, all the impulses from 5 to infinity, that gives you the step response. Okay, great. So can I go the other way? Yeah, you could go the other way, and that's simply a derivative. So a unit impulse function is basically the derivative of the step function. So that basically, if you look at the derivative of a step function, the only time it has a non-zero derivative is right where it changes. For example, for this one, since we did it at 0, a unit step function looks like this at 0. And if you take a derivative of it, it's going to be 0, and the only place it's going to be non-zero is right here. Okay. And it says, we said that the magnitude is basically 1, and the only place it presents itself is at 0. Okay, so that's a step function. Great. So let's do one thing before we go away. Let's say, are we able to draw? So as an example, we want to draw. We want to draw a function. Let's say the function is x of t is equal to 3u t plus 5. I'm going to do something different this time. Plus 3 delta t plus 7. I'm going to make it all go that way. So if you look at this one, this is basically saying this is non-zero when t is larger or equal to minus 5. This is saying it's only non-zero when t is equal to minus 7. So if you plot this one and get all those impacts going, the impulse is going to basically the step function is just going to come to minus 5, and then it's going to pop up and go to infinite. And this effect of the impulse response is that at minus 7 it pops up, and that's about it. And the magnitude here is 3, magnitude here is 3 also. So that's an example of how we may use these two new functions we've learned to describe a graph or a function that we have to work with.